Okay, so we're looking at the orthonormal basis problems. Um, and the first set here asks us, if I give you a set of vectors, can you tell me if the set is orthogonal, orthonormal, or neither? Alright, so in problem number 1, we get the vectors negative 4, 6, and 5, 0. So the first thing we do is we check orthogonality. So we're going to take negative 4, 6 and take the dot product with 5, 0. That's going to give me negative 20 plus 0, which is negative 20, which is not 0. So we are not orthogonal. If we can't be orthogonal, then we can't be orthonormal. So this is a case where we would say that it is I'm spelling really well today. Neither, neither. There we go. So this is neither orthogonal nor orthonormal. All right, so let's look at number 2. Also in R2, we have the 3/5, 4/5, negative 4/5. So let's write these out. 3/5, 4/5, negative 4/5, 3/5. So again, the first thing to do is to take the dot product, right? So you need 3/5, 4/5, dot negative 4/5, 3/5, which works out to be 12/25 negative plus 12/25 positive, which comes out as 0. So at this point, we know that we're orthogonal. Okay. Orthonormal would mean that both vectors have a magnitude of 1. So let's take a magnitude of the 3/5, 4/5 vector. So this is square root of 9/25 plus 16/25, which is the square root of 25/25, which is 1. So that's good. Or we take negative 4/5, 3/5, which is square root of 16/25 plus 9/25, which is also 25/25, which is 1. So this is both orthogonal. Everything has a magnitude of 1. So we say that we are orthonormal. Orthonormal. Alright, so we're orthogonal or orthonormal. That's number 2. Let's move on to number 3. Alright, number 3, we're three-dimensional vectors. We're in R3. And we have 3 vectors. So what we need to do here is we need to check all the dot products. So there's 3 possible dot products here. If we take 4, negative 1, 1, and dot that with negative 1, 0, 4, that's going to give me negative 4 plus 0 plus 4, which is 0. So those two are orthogonal. 4, negative 1, 1, dotted with negative 4, negative 17, negative 1. That's going to give me 16 plus 17, negative 16 plus 17 minus 1. That comes out as 0. So those two are orthogonal. And negative 1, 0, 4, dotted with negative 4, negative 17, negative 1, gives me 4, 0, negative 4. So that one also comes out as 0. So all of the vectors are orthogonal to each other. Now, it's really simple here to disprove orthonormality, because if I just use the 4, negative 1, 1, the magnitude of that is going to be 16 plus 1 plus 1, which is the square root of 17, which is not 1. So this is orthogonal, but not orthonormal. Looking at number 4, we are still in R3. So let's grab the first 2 vectors that are there. We have root 2 over 3, 0, negative root 2 over 6, and we're going to dot that with 0, 2 radical 5 over 5, negative radical 5 over 5. All right. So the first one gets me 0. The second one gets me 0. And then I've got positive square root of 10 over 30. So that dot product is a positive square root of 10 over 30, which is not 0. Which means I'm not orthogonal. Which means I cannot be orthonormal. So this is a case where I am neither. All right, so let's move on to number 5. All right, so 5 is 3 vectors that are in R4. All right, so we've got root 2 over 2, 0, 0, root 2 over 2. And we're going to dot that with 0, root 2 over 2, root 2 over 2, 0, right? So all 4 of the components here in the dot product come out as 0, which means that that's orthogonal. All right, so let's try the second one. We have root 2 over 2, 0, 0, root 2 over 2. And we're going to dot this with negative a half, negative a half, a half. So the first one comes out as negative root 2 over 4 plus 0 plus 0 plus root 2 over 4. So that comes out as 0. So those two vectors are orthogonal. Next one is 0 root 2 over 2, root 2 over 2, 0, and we're going to dot that with the negative half, negative a half, half. So that's going to give me 0 root 2 over 4 minus root 2 over 4 plus 0, which is back to 0. So all 3 vectors are orthogonal to each other. Now we've got to check their magnitudes. So if I take the magnitude of root 2 over 2, 0, 0, root 2 over 2, I end up with square root of, let's see, that's 2 fourths, plus 0 plus 0 plus 2 fourths is the square root of 1, which is 1, so that works. This one works very similarly. Root 2 over 2, 0, so this is going to be square root of 0 plus 2 fourths plus 2 fourths plus 0, which again is 1. And the last one is negative a half, negative a half, which is a fourth plus a fourth plus a fourth plus a fourth, which is 1. So all of them are orthogonal. They're all unit vectors, so we say that this is orthonormal. All right, so let's move on to number 6. Okay, problem 6 changes my vector space to P3. So polynomials of degree 3. We have a series of 4 vectors here, which means we got to check 6 orthogonalities. If I take 1 by x, that's going to give me 0. 1 by x squared is also 0. 1 by x cubed, dot product is 0. X by x squared gives me 0. X by x cubed gives me 0. X squared by x cubed is going to give me 0, so they're all orthogonal to each other. If I take the magnitude of each one, I do get 1. And finally, so this means that I'm orthonormal, and since the dimension of the set is 4, and the dimension of the size of the set, the size of the set is 4, right? And the dimension of P3 is also 4. I have right size, I have orthogonal, I have normal, so I can say that this is an orthonormal basis. for P3. And in fact, this is the standard basis for P3. So there you go. So last problem here, we're going to give you a non-standard basis for R2. And we're going to show that that is a non-standard orthonormal basis for R2. And it doesn't matter what theta is, right? So if I dot product these, right? So I'm going to take sine theta, cosine theta, dot cosine theta, negative sine theta. My dot product comes out as sine theta cosine theta minus cosine theta sine theta, and regardless of what theta is, that's 0. So these vectors are orthogonal regardless of what the measure of theta is. So now we want to prove normalcy, right? So we got sine, take the magnitude of sine theta cosine theta, which becomes square root of sine squared theta plus cosine squared theta, which is square root of 1, which is 1. So that's a unit vector. Likewise, cosine theta, negative sine theta, magnitude becomes square root cosine squared theta plus sine squared theta, which is square root of 1, which is 1. So that's also a unit vector. We're looking at R2. The dimension of R2 is 2. So I have right size. I have orthonormal. So this is an orthonormal basis for R2. Awesome. Thank you. All right. Hope that this helps you. Thank you.